3.6, we look at the derivatives of logs and other exponentials. So by other exponentials, we mean any exponential that is not e to the x. So if you've got a different number, 2 to the x, 3 to the x, things like that. Most of our attention here, though, is on logarithms. So I thought it'd be a good idea to begin just a really quick overview recap of logs in the way that will be useful for us. So let's start with this. The definition of the logarithm is what you see right here. Y equals the log of x with base a is interchangeable with, or you might say it's equivalent to, x equals a raised to the y. And okay, I also just wrote out how you exactly speak this. The log of x with base a is your subscript, right? Okay, so let's practice the definition of the logarithm. Logarithms tend to give people a tough time. I think this will be a good idea. Okay, so let's say, what if we were told that 3 equals the log of x with base 4, and we wanted to know the value of x? We'd say, oh, okay, so the y is 3, the a is 4. Let me rewrite it this way. And we'd say, oh, so then x equals 4 raised to the third, or in other words, x equals 64, if we were to solve that for x. All right. Another good question is, very pertinent for us, what is the domain of a logarithm? So if you think of it as a function, f of x equals the log of x with base a. So it turns out any logarithm like that has the same basic shape and the same domain. Here it is. So there's always this vertical asymptote happening at 0, and the log will approach negative infinity from this side. As it comes up, it's always going to pass through 1 and then continue up, and although it levels off, it appears to level off, it does increase forever. So thinking of the domain, any logarithm has the domain from 0, not including 0, to infinity, just the positive numbers. Of course, you can shift a log up or down or to the left or whatever. You could take a reflection, back here, or a mirror image this way, but the domain of just the regular old log, 0 to infinity. Finally, I know you guys know this, but let's just say it anyway. There are two special logarithms, the common log and the natural log. The common log is written as simply the log of x. If the base is not written, then it's implied to be 10. And the natural log, written this way, ln of x. That has a base of e. And you might be wondering why the letters get reversed. NL, ln. Pretty sure this is Latin in its original origins. And so in those languages, the adjective is always placed second, logarithm natural. Okay, has base e. All right. So how is this section going to unfold? We're going to begin with this question. What is the derivative of the natural log of x? We begin with natural log x because we already know the derivative for e to the x, and that's going to be helpful to get this one. Okay, how are we going to go about discovering this derivative? It's actually a brand new approach. We're not going to do it with the definition of the derivative. We're not going to do it by graphing. Here's how it's going to go down. Since we know the derivative of e to the x, we're going to do this. We're going to begin with a true statement. So take a moment, look at that, and hopefully you agree that e raised to the natural log of x is equal to x, right? E and natural log cancel out. Okay, so beginning with that true statement, we're going to apply a derivative to both sides. Well, okay, well, that would have to follow logically, right? Yeah. Now, if you look closely at the left, e raised to the natural log of x. So we know the derivative for e, but not this. So it's pretty clever how this unfolds. Also, this would be a chain rule, right? This would be the inside, and e is the outside. So, thinking of the chain rule here, here's how it would go. The derivative of the e, well, we just copy everything. Okay. Then we would multiply by the derivative of the inside, d over dx, applied to natural log of x. Now, of course, we don't know what this is. That's the whole question in the first place. So we'll just leave it like that. Okay, so we've got e to the natural log of x times the derivative of natural log x, which we don't know. And on the right side, well, that's equal to 1. So if we want to know what this equals, all we got to do is divide this over to the other side. And that is pretty clever. So let's divide it over. And it turns out we don't have to be satisfied with this 1 over e to the natural log of x. Well, certainly that's what happens when you divide. But hey, isn't e to the natural log of x just equal to x? And oh yeah, well, yeah, that was just equal to x the whole time. So, yep, the derivative for the natural log of x equals 1 over x. And now we have a new rule for this derivative. Okay, let's pause before we go on. Just do a couple of examples, get used to this idea. A couple of derivatives. So, let's say f of x equals x to the third times the natural log of x. Let's find f prime. You think, okay, well, we know this, so we're good to go. This is a product rule, right? So here it is. Derivative of my first part times the second part left alone, plus my first part times the derivative of natural log x, which we now know to be 1 over x. There's our product rule. And we can simplify this pretty nicely. Here we get some cancellation. Our final answer, 3x squared natural log x plus x squared. There it is. Okay, let's see another example. That was a nice product rule. This one's going to have a chain rule. Just ignore what I've got going on here for the moment. Let's say g of x equals the natural log of tangent x. Okay, how is it going to work? There's a chain rule here. Natural log is the outside. Tan x is the inside, and it's literally inside the parentheses, which is nice. Okay, so chain rule. We take the derivative of the outside first. Then we'll multiply by the derivative of the inside. How's that going to go down? Here it is. The derivative of a natural log is always 1 over what we call the argument, which is here the inside. So a lot of people get tripped up with this. They're like 1 over tangent x, like, oh, and you know, that gives people a tough time. Think of it like this. So if I simply had natural log of x, the derivative is 1 over x, of course. So if there's something more complicated than just x in here, then that gets replaced. So here we go. Whatever is inside, that goes underneath the 1. Okay? So if it's x, then it's 1 over x. But if it's the natural log of tangent x, then the derivative of the natural log is 1 over the tangent x. And then we multiply by the derivative of tangent x, which we know to be secant squared x. So the outside, take 1 over whatever's in here, and then multiply by your derivative of that. There's your chain rule. Now this one you can simplify. 1 over tangent x happens to be cotangent of x. So we might as well just write that. I'm going to keep this the same. There might be some further simplification that could happen. I'm not going to go there. This looks good to me. Okay, very nice. Let's stop this video here. In the next one, we're going to explore the derivatives of other types of logs besides natural log.